Okay, this is 5.3 of geometry. When three or more lines intersect at one point, they are concurrent. And the point which they intersect at is called the point of concurrency. So when three lines intersect, they are concurrent. When they intersect at one point, they are concurrent. And the point at which they intersect is the point of concurrency. So, our theorem here, if we take the perpendicular bisectors, so remember perpendicular bisector means it's perpendicular and it splits the side in half, right? It's at the midpoint. So if we take the perpendicular bisector of each side, so here's one, and here's one, right? And you can see the markings. They all have that right angle marked, so they're perpendicular. And they all have their markings that says that it's the midpoint. So if we have if we take the perpendicular bisectors of each side, they are concurrent. And you can see here they're concurrent at the point P right there. They all meet right there. Well, it just so happens that if you take the perpendicular bisectors of the sides, then they make these blue guys here that are congruent. So if you take a vertex, one of the corners of the triangle, and you connect it all at point P, where they're concurrent, those sides are all congruent. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Those are all congruent. Okay, the point of concurrency of the perpendicular bisectors, so the point P over here in the middle, that is called the circumcenter of the triangle. And since it is equidistant from the vertices, right? It's the same distance here. That's the same distance. That's the same distance. We can draw a circle around it, and those are radii, or radiuses. So we can take a circle, and it is circumscribed about the triangle. Okay, when we're looking at circumcenters, if it's a acute triangle, the circumcenter is inside of the triangle. If it's a right triangle, it's going to be on our hypotenuse. And if it's an obtuse triangle, the circumcenter is going to be outside the triangle. Okay, what are the coordinates of the circumcenter of the triangle with vertices A, B, and C? So I'm going to put these on the graph first. So 1, 2, and 1, 2, 3, 4, 5, 6, 7. There's A. B is at 10, 7. And C is at 10, 3. Okay, so here's my triangle. Move C a little closer. So I need to find the perpendicular bisector. So the first thing I'm going to do is I'm going to find the midpoints. So there's a midpoint. Oops. And there's a midpoint. Here's the deal though. We know perpendicular bisectors are always going to meet up together, right? They're always going to be concurrent. So do I need to do all three of them? No. I only have to do 2 of them because I know they're always going to meet up. It's not like one of these times I'm going to draw 3 and shoot. They don't meet up. They're always going to meet up at the same point. So I only need 2 lines to show me where they're going to meet up. When we're working with right triangles and they're going up and down and left and right, it's really easy to make a perpendicular bisector, right? because a horizontal and a vertical line are perpendicular. Otherwise, if I don't have a right triangle, I need to calculate the slope of this line, and I need to figure out the perpendicular slope, and I need to figure out the equation and graph it. So I'm going to make my life easier. I'm just going to graph in these perpendicular bisectors. So here's one. That's perpendicular, and it goes on forever, right? And here's another. It's perpendicular. So the circumcenter of this triangle is located right there, and those coordinates are 1, 2, 3, 4, 5, 6, comma, 1, 2, 3, 4, 5, 6, 5. So I drew in the perpendicular bisectors and I found out where they met up. Okay, so the town planner wants to place a bench equidistant from the 3 trees in the park. Where should he place the bench? So I'm not going to do this exactly, but I am going to sketch it in for you. So here's our triangle, right? If we want it equidistant from each of these, it's going to be something like this, right? Choose a point. I need these to be congruent. Well, that's what my circumcenter gives me. If I can find the circumcenter, I know that the distance from the circumcenter to the vertices are all congruent. So remember, I use perpendicular bisectors to find my circumcenter. So I'm going to find my midpoint. That's about there. And remember, I only need to do it on 2. About there. I'm going to try to draw that in perpendicular. Draw it in perpendicular. We'll just say that my estimations are correct. Right there on my blue point is where they should put the bench then. Okay. The concurrency of angle bisectors theorem. So, we were looking at perpendicular bisectors, right? They're perpendicular to a side and it's through the midpoint, splits it into 2 equal parts. That's a perpendicular bisector. Now we're going to look at the angle bisectors. So, they drew in the angle bisectors here, right? A bisector splits it into 2 equal angles. So these are all angle bisectors. And they're concurrent at point P. This is where they all meet up. And if we connect from P perpendicular to the side, all these lines are equal. We call this the in-center of the triangle. And the in-center is always going to be inside of the triangle. It'll always be located inside. It's not located outside if it's obtuse. It'll always be located inside. So the in-center is always inside of our triangle, and that's with our angle bisectors. With our other one, we were putting a circle on the outside of the triangle, right? Like this. Now, with an in-center, we can inscribe a circle inside of the triangle and use these guys as radius. Or radii. So the in-center. Okay, so if we look at theirs, I'm going to start labeling it with colors here. Here's an angle bisector, here's an angle bisector, and here's an angle bisector. So G is the point of concurrency. I know by my theorem that these guys, because they're drawn perpendicular there, are equal. So in this one I'm told GE is equal to 2x minus 7 and GF is equal to x plus 4. So I can solve for x and set them equal to each other. I know they must be equal because they're congruent. So I would do 2x minus 7 is equal to x plus 4. Add 7 to both sides. 2x is equal to x plus 11. minus x, and I get x equals 11. They want to know what GD is, but I wasn't given an expression for GD. They didn't tell me something I could plug into. But I know that GD is equal to GE and to GF, so I can just plug into one of those. So I'm going to plug into this one. 11 plus 4, that gives me 15. So GD is equal to 15. Okay, let's try one on our own down here. So a couple extra lines drawn in here. So I'm going to use blue to draw my angle bisectors in. Got an angle bisector here. I've got an angle bisector here. I don't have one there. I mean, I could sketch one in, but I know that I only need 2 lines to figure out that point of concurrency because I know they're going to be concurrent there. So Q is where they're concurrent. So then I know that these guys here are equal. So I'm told that QN is 5x plus 36. And that QM is 2x plus 51. I know those are congruent, so I'm going to set them equal to each other. 5x plus 36 is equal to 2x plus 51. I'll subtract 2x from both sides, which gives me 3x plus 36 equals 51. Subtract 36 from both sides. Ran out of room, so I'm going to move it over here. I get 3x is equal to 15. Divide by 3. And x equals 5. They want to know what QO is. Well, I don't have an expression for QO, but I know that it's congruent to QN and QM. So I'm just going to plug into one of those, and I'll plug in over here. We'll do 2 times 5 plus 51. So that's 10 plus 51. So that's 61. So QO is equal to 61. As is all the other ones, right? QN is also 61 and QM is also 61. And there's your homework.